Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Cloud Architect certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You are creating a solution to remove backup files older than 90 days from your backup cloud storage bucket. You want to optimize ongoing cloud storage spend. What should you do? The options are: Option A, write a lifecycle management rule in XML and push it to the bucket with SUDL. Option B, write a lifecycle management rule in JSON and push it to the bucket with SUDL. Option C, schedule a cron script using SUDL lslrgs //backup/ to find and remove items older than 90 days. Option D, schedule a cron script using SUDL lslgs //backup/ to find and remove items older than 90 days and schedule it with cron.
To arrive at the correct answer, we focus on the keywords: remove backup files older than 90 days, optimize ongoing cloud storage spend.
The correct answer is option B, write a lifecycle management rule in JSON and push it to the bucket with SUDL.
Why is this correct? B. Cloud storage lifecycle management natively automates deleting objects older than 90 days to optimize spend. The configuration file for lifecycle rules applied via SUDL must be written in JSON format. Why are the others incorrect? A. Lifecycle management rules for cloud storage buckets must be written in JSON format, as XML is not supported for SUDL lifecycle configuration files. C. Using a cron script to list and delete files requires continuous compute resources and incurs unnecessary API call overhead compared to native lifecycle rules. D. Scheduling a custom cron script adds unnecessary operational complexity, management overhead, and compute costs compared to built-in object lifecycle management.
Your company is forecasting a sharp increase in the number and size of Apache Spark and Hadoop jobs being run on your local data center. You want to utilize the cloud to help you scale this upcoming demand with the least amount of operations work and code change. Which product should you use? The options are: Option A, Google Cloud Dataflow. Option B, Google Cloud Data Proc. Option C, Google Compute Engine. Option D, Google Kubernetes Engine.
To arrive at the correct answer, we focus on the keywords: Apache Spark and Hadoop jobs, least amount of operations work, code change.
The correct answer is option B, Google Cloud Data Proc.
Why is this correct? B. Google Cloud Data Proc is a fully managed service for running Apache Spark and Apache Hadoop workloads, enabling seamless migration of existing jobs with minimal operational overhead and no code changes. Why are the others incorrect? A. Google Cloud Dataflow is based on Apache Beam, requiring code rewriting to migrate existing Apache Spark and Hadoop pipelines. C. Google Compute Engine requires manual provisioning, configuration, and management of Hadoop and Spark clusters, leading to high operational effort. D. Google Kubernetes Engine requires containerizing workloads and managing Kubernetes manifests, resulting in significant operational overhead compared to a managed Hadoop service.
The database administration team has asked you to help them improve the performance of their new database server running on Google Compute Engine. The database is for importing and normalizing their performance statistics and is built with MySQL running on Debian Linux. They have an N1 standard 8 virtual machine with 80 GB of SSD persistent disk. What should they change to get better performance from this system? The options are: Option A, increase the virtual machine's memory to 64 GB. Option B, create a new virtual machine running PostgreSQL. Option C, dynamically resize the SSD persistent disk to 500 GB. Option D, migrate their performance metrics warehouse to BigQuery. Option E, modify all of their batch jobs to use bulk inserts into the database.
To arrive at the correct answer, we focus on the keywords: improve the performance, Google Compute Engine, 80 GB of SSD persistent disk.
The correct answer is option C, dynamically resize the SSD persistent disk to 500 GB.
Why is this correct? C. Persistent disk performance in Compute Engine scales linearly with disk capacity. Dynamically increasing the SSD disk size to 500 GB significantly improves read and write IOPS and throughput. Why are the others incorrect? A. While increasing memory helps, N1 Standard 8 already has 30 GB RAM. Disk I/O is the primary bottleneck for an 80 GB disk, making disk resizing more directly impactful for performance. B. Switching database engines to PostgreSQL requires a major migration and application refactoring without addressing the fundamental disk I/O performance limitation of small persistent disks. D. Migrating to BigQuery requires changing the entire database architecture and application logic, whereas the question specifically asks to improve the performance of their current compute engine system. E. Modifying application code for bulk inserts can help application throughput, but expanding disk capacity directly resolves the core infrastructure bottleneck by boosting underlying persistent disk IOPS.
You want to optimize the performance of an accurate, real-time, weather charting application. The data comes from 50,000 sensors sending 10 readings a second, in the format of a timestamp and sensor reading. Where should you store the data? The options are: Option A, Google BigQuery. Option B, Google Cloud SQL. Option C, Google Cloud Bigtable. Option D, Google Cloud Storage.
To arrive at the correct answer, we focus on the keywords: real-time, 50,000 sensors sending 10 readings a second, timestamp and sensor reading.
The correct answer is option C, Google Cloud Bigtable.
Why is this correct? C. Google Cloud Bigtable is optimized for high throughput, low latency writes and time series data, making it ideal for handling 500,000 sensor readings per second in real time. Why are the others incorrect? A. BigQuery is an analytical data warehouse suited for OLAP, not for low latency, high frequency real-time write workloads at 500,000 records per second. B. Cloud SQL is a relational database service that cannot scale horizontally to support the massive scale of 500,000 write operations per second. D. Cloud Storage is an object storage service designed for blob data and files, making it unsuitable for high-frequency time series database writes.
Your company's user feedback portal comprises a standard LAMP stack replicated across 2 zones. It is deployed in the Central 1 region and uses auto-scaled managed instance groups on all layers, except the database. Currently, only a small group of select customers have access to the portal. The portal meets a 99.99% availability SLA under these conditions. However, next quarter, your company will be making the portal available to all users, including unauthenticated users. You need to develop a resiliency testing strategy to ensure the system maintains the SLA once they introduce additional user load. What should you do? The options are: Option A, capture existing users' input and replay captured user load until autoscale is triggered on all layers. At the same time, terminate all resources in one of the zones. Option B, create synthetic random user input, replay synthetic load until autoscale logic is triggered on at least one layer, and introduce chaos to the system by terminating random resources on both zones. Option C, expose the new system to a larger group of users, and increase group size each day until autoscale logic is triggered on all layers. At the same time, terminate random resources on both zones. Option D, capture existing users' input and replay captured user load until resource utilization crosses 80%. Also, derive estimated number of users based on existing users' usage of the app, and deploy enough resources to handle 200% of expected load.
To arrive at the correct answer, we focus on the keywords: availability SLA, unauthenticated users, resiliency testing strategy.
The correct answer is option B. Create synthetic random user input, replay synthetic load until autoscale logic is triggered on at least one layer, and introduce chaos to the system by terminating random resources on both zones.
Why is this correct? B. Generating synthetic load with random user input simulates new, unauthenticated traffic patterns. Introducing chaos engineering by terminating random resources across both zones effectively tests system resiliency, fault tolerance, and autoscaling capabilities required to sustain the SLA. Why are the others incorrect? A. Replaying existing user input fails to model unauthenticated user behavior, and taking down an entire zone at once is less granular than chaos testing across both zones. C. Exposing real users to untested loads risks violating SLAs on production systems instead of testing resiliency in a controlled synthetic environment. D. Replaying current user input does not represent unauthenticated user patterns, and static over-provisioning, 200% capacity, does not validate autoscaling or system resiliency under failure.
Your solution is producing performance bugs in production that you did not see in staging and test environments. You want to adjust your test and deployment procedures to avoid this problem in the future. What should you do? The options are: Option A, deploy fewer changes to production. Option B, deploy smaller changes to production. Option C, increase the load on your test and staging environments. Option D, deploy changes to a small subset of users before rolling out to production.
To arrive at the correct answer, we focus on the keywords: performance bugs in production, staging and test environments. Adjust your test and deployment procedures.
The correct answer is option C. Increase the load on your test and staging environments.
Why is this correct? C. Performance bugs appearing only in production usually stem from staging and test environments lacking realistic, production-level traffic. Increasing the load during testing helps simulate real-world usage and catch scale-related bottlenecks before deployment. Why are the others incorrect? A. Deploying fewer changes reduces deployment frequency but fails to address the underlying issue of pre-production environments not matching production load. B. Deploying smaller changes aids in troubleshooting and reduces risk, but it does not help identify high-traffic performance bugs during pre-production testing. D. Deploying to a subset of users, canary release, limits the blast radius of bugs, but it does not improve pre-production test procedures to catch issues prior to release.
A small number of API requests to your microservices-based application take a very long time. You know that each request to the API can traverse many services. You want to know which service takes the longest in those cases. What should you do? The options are: Option A, set timeouts on your application so that you can fail requests faster. Option B, send custom metrics for each of your requests to Stackdriver Monitoring. Option C, use Stackdriver Monitoring to look for insights that show when your API latencies are high. Option D, instrument your application with Stackdriver Trace in order to break down the request latencies at each microservice.
To arrive at the correct answer, we focus on the keywords: microservices-based application, traverse many services, which service takes the longest.
The correct answer is option D. Instrument your application with Stackdriver Trace in order to break down the request latencies at each microservice.
Why is this correct? D. CloudTrace, formerly Stackdriver Trace, is a distributed tracing system that collects latency data from microservices and displays it in detailed end-to-end request traces, allowing you to pinpoint which specific service causes delays. Why are the others incorrect? A. Setting timeouts helps fail slow requests faster to prevent cascading failures, but it does not identify which specific microservice is causing the delay. B. Sending custom metrics to Stackdriver Monitoring tracks aggregated performance metrics over time, but it lacks the distributed context needed to trace individual request flows across services. C. Stackdriver Monitoring helps visualize overall system health and set latency alerts, but it cannot break down individual request latencies across interconnected microservices.
During a high-traffic portion of the day, one of your relational databases crashes, but the replica is never promoted to a master. You want to avoid this in the future. What should you do? The options are: Option A, use a different database. Option B, choose larger instances for your database. Option C, create snapshots of your database more regularly. Option D, implement routinely scheduled failovers of your databases.
To arrive at the correct answer, we focus on the keywords: relational databases crashes, replica is never promoted to a master. Avoid this in the future.
The correct answer is option D, implement routinely scheduled failovers of your databases.
Why is this correct? D. Routinely scheduling failovers tests and validates the automated failover mechanism under controlled conditions, ensuring that replicas can be successfully promoted to master during an actual unpredicted outage. Why are the others incorrect? A. Switching database engines does not inherently fix replica promotion configurations or guarantee that failover mechanisms work properly. B. Increasing instance size helps handle higher traffic loads to reduce crash frequency, but it does not fix the issue of a replica failing to promote when a crash occurs. C. Frequent snapshots reduce potential data loss during manual restoration, but they do not automate or facilitate the high availability failover process.
Your organization requires that metrics from all applications be retained for 5 years for future analysis in possible legal proceedings. Which approach should you use? The options are: Option A, grant the security team access to the logs in each project. Option B, configure Stackdriver monitoring for all projects and export to BigQuery. Option C, configure Stackdriver monitoring for all projects with the default retention policies. Option D, configure Stackdriver monitoring for all projects and export to Google Cloud Storage.
To arrive at the correct answer, we focus on the keywords: retained for 5 years, future analysis, legal proceedings.
The correct answer is option D, configure Stackdriver monitoring for all projects and export to Google Cloud Storage.
Why is this correct? D. Google Cloud Storage provides a cost-effective solution for long-term retention of exported metrics over a 5-year period for compliance and legal requirements. Why are the others incorrect? A. Granting access to logs does not configure metric exports or solve long-term metrics retention requirements. B. Exporting metrics to BigQuery for long-term 5-year archival is significantly more expensive than storing cold data in Google Cloud Storage. C. Default cloud monitoring retention for metrics is only 6 weeks, 42 days, which is far short of the required 5 years.
Your company has decided to build a backup replica of their on-premises user authentication PostgreSQL database on Google Cloud Platform. The database is 4 terabytes, and large updates are frequent. Replication requires private address space communication. Which networking approach should you use? The options are: Option A, Google Cloud Dedicated Interconnect. Option B, Google Cloud VPN connected to the data center network. Option C, a NAT and TLS translation gateway installed on-premises. Option D, a Google Compute Engine instance with a VPN server installed connected to the data center network.
To arrive at the correct answer, we focus on the keywords: PostgreSQL database, 4 terabytes, large updates are frequent, private address space communication.
The correct answer is option A, Google Cloud Dedicated Interconnect.
Why is this correct? A. Dedicated Interconnect provides a high-capacity, low-latency private connection directly to Google Cloud, making it the best choice for transferring high volumes of data with frequent large updates securely over private IP space. Why are the others incorrect? B. Cloud VPN operates over the public internet and has lower bandwidth limits, making it inefficient and too slow for frequent large updates to a 4 terabytes database. C. A NAT and TLS translation gateway does not establish a dedicated, high-throughput private network connection required for large-scale database replication. D. Running a custom VPN server on a compute engine instance introduces bandwidth bottlenecks, high maintenance overhead, and reliability risks compared to dedicated interconnect.
Auditors visit your teams every 12 months and ask to review all the Google Cloud Identity and Access Management (Cloud IAM) policy changes in the previous 12 months. You want to streamline and expedite the analysis and audit process. What should you do? The options are: Option A, create custom Google Stackdriver alerts and send them to the auditor. Option B, enable logging export to Google BigQuery and use ACLs and views to scope the data shared with the auditor. Option C, use Cloud Functions to transfer log entries to Google Cloud SQL and use ACLs and views to limit an auditor's view. Option D, enable Google Cloud Storage (GCS) log export to audit logs into a GCS bucket and delegate access to the bucket.
To arrive at the correct answer, we focus on the keywords Cloud IAM, previous 12 months, streamline and expedite the analysis and audit process.
The correct answer is option B, enable logging export to Google BigQuery and use ACLs and views to scope the data shared with the auditor.
Why is this correct? B. Exporting audit logs to BigQuery allows for rapid analytical querying of 12 months of log data. Using BigQuery dataset permissions and authorized views enables secure, scoped access for auditors to analyze policy changes efficiently. Why are the others incorrect? A. Stackdriver, cloud logging. Alerts are designed for real-time notifications of active events, not for querying and analyzing historical log data over a 12-month period. C. Using Cloud Functions to stream logs to Cloud SQL introduces unnecessary architectural complexity and maintenance overhead compared to native log export features. D. Exporting to cloud storage is ideal for long-term cold storage archiving, but analyzing raw log files in GCS is inefficient compared to querying data in BigQuery.
You are designing a large distributed application with 30 microservices. Each of your distributed microservices needs to connect to a database backend. You want to store the credentials securely. Where should you store the credentials? The options are: Option A, in the source code. Option B, in an environment variable. Option C, in a secret management system. Option D, in a config file that has restricted access through ACLs.
To arrive at the correct answer, we focus on the keywords distributed application, 30 microservices, store the credentials securely.
The correct answer is option C, in a secret management system.
Why is this correct? C. A secret management system securely stores, rotates, audits, and controls access to sensitive credentials across distributed microservices. Why are the others incorrect? A. Hardcoding credentials in source code creates severe security risks and exposes sensitive data via source control. B. Environment variables lack centralized auditing, rotation features, and can easily leak through process logs or system dumps. D. Local configuration files are difficult to sync and secure across 30 microservices and lack automated rotation and fine-grained auditing capabilities.
A lead engineer wrote a custom tool that deploys virtual machines in the legacy data center. He wants to migrate the custom tool to the new cloud environment. You want to advocate for the adoption of Google Cloud Deployment Manager. What are 2 business risks of migrating to Cloud Deployment Manager? Choose 2. The options are: Option A, Cloud Deployment Manager uses Python. Option B, Cloud Deployment Manager APIs could be deprecated in the future. Option C, Cloud Deployment Manager is unfamiliar to the company's engineers. Option D, Cloud Deployment Manager requires a Google API service account to run. Option E, Cloud Deployment Manager can be used to permanently delete cloud resources. Option F, Cloud Deployment Manager only supports automation of Google Cloud resources.
To arrive at the correct answer, we focus on the keywords custom tool, legacy data center, Google Cloud Deployment Manager, business risks.
The correct answers are option C, Cloud Deployment Manager is unfamiliar to the company's engineers, and option F, Cloud Deployment Manager only supports automation of Google Cloud resources.
Why is this correct? C. Adoption introduces a learning curve and training overhead because the internal engineering team is unfamiliar with Deployment Manager's templates and syntax. F. Deployment Manager is vendor-locked to Google Cloud, preventing its use for managing legacy data center resources or multi-cloud environments. Why are the others incorrect? A. Supporting Python or Jinja 2 is a standard technical feature of Deployment Manager, not an inherent business risk. B. Core Google Cloud APIs follow strict deprecation policies, making sudden API deprecation an unlikely and standard non-factor. D. Using service accounts for authentication is a standard GCP security requirement, not a business risk. E. Resource deletion is standard for IAC tools and is controlled through proper IAM roles and safeguards, not a unique risk.
Development Manager is building a new application. He asks you to review his requirements and identify what cloud technologies he can use to meet them. The application must 1. Be based on open-source technology for cloud portability. 2. Dynamically scale compute capacity based on demand. 3. Support continuous software delivery. 4. Run multiple segregated copies of the same application stack. 5. Deploy application bundles using dynamic templates. 6. Route network traffic to specific services based on URL. Which combination of technologies will meet all of his requirements? The options are Option A, Google Kubernetes Engine, Jenkins, and Helm. Option B, Google Kubernetes Engine and Cloud Load Balancing. Option C, Google Kubernetes Engine and Cloud Deployment Manager. Option D, Google Kubernetes Engine, Jenkins, and Cloud Load Balancing.
To arrive at the correct answer, we focus on the keywords: open source technology, dynamically scale compute capacity, continuous software delivery, deploy application bundles using dynamic templates.
The correct answer is option A, Google Kubernetes Engine, Jenkins, and Helm.
Why is this correct? A. Google Kubernetes Engine provides open-source container orchestration, autoscaling, and URL routing. Jenkins enables continuous software delivery. Helm fulfills the requirement for deploying application bundles using dynamic templates and managing segregated application stacks. Why are the others incorrect? B. This combination lacks Jenkins for continuous software delivery and Helm for packaging application bundles with dynamic templates. C. Cloud Deployment Manager is a GCP proprietary infrastructure tool that lacks continuous delivery capabilities and open-source application templating like Helm. D. While this includes Jenkins and GKE, it lacks Helm, which is required to deploy application bundles using dynamic templates.
You have created several preemptible Linux virtual machine instances using Google Compute Engine. You want to properly shut down your application before the virtual machines are preempted. What should you do? The options are: Option A, create a shutdown script named k99.shutdown in the /etc/rc.6.d/directory. Option B, create a shutdown script registered as a Zinit service in Linux and configure a Stackdriver endpoint check to call the service. Option C, create a shutdown script and use it as the value for a new metadata entry with the key shutdown script in the Cloud Platform console when you create the new virtual machine instance. Option D, create a shutdown script, registered as a Zinit service in Linux, and use the Cloud Compute Instance's add metadata command to specify the service URL as the value for a new metadata entry with the key shutdown script URL.
To arrive at the correct answer, we focus on the keywords: preemptible Linux virtual machine, shut down your application before the virtual machines are preempted.
The correct answer is option C, create a shutdown script and use it as the value for a new metadata entry with the key shutdown script in the Cloud Platform console when you create the new virtual machine instance.
Why is this correct? C. Compute engine executes shutdown scripts before preempting or terminating an instance. Adding the script as metadata with the key shutdown script ensures GCP executes it automatically during the preemption grace period. Why are the others incorrect? A. Placing scripts in OS run level directories like /etc/rc.6.d/ does not integrate directly with GCP's metadata system for preemption notification management. B. Stackdriver endpoint checks are designed for monitoring availability, not for executing internal shutdown scripts on preempted VM instances. D. The metadata key shutdown script URL expects a URL pointing to a storage bucket or file path containing the script, not a Zinit service URL.